Okay, hi everyone. Thank you for coming down this afternoon. Today's speaker is Laurence Levasseur, and she'll correct me for butchering her name.
No, it's all good. You're doing super well.
So she is a professor at the University of Montreal and did her PhD in Cambridge, working on inflation, and was then a postdoc and a visiting researcher, and a scientist at Stanford and Flatiron Institute in New York. So please welcome Laurence today.
Hi. Does this work? Not really. Okay. Maybe I should try to put it somewhere better. Sorry about that. Is it better here? Yeah. Okay. All right. Great. So thank you for the invitation. It's really a pleasure to be in Oxford. Today, like you probably guessed from my title, I'm going to be talking about machine learning and strong gravitational lensing. So what I'm going to be talking about is based on those 4 papers here. So first, I'd like to acknowledge my collaborators, Yashar Hezave and Warren Morningstar, who was a PhD student at Stanford at the time that this was completed. And and also Yeringal, who is faculty here, and Max Welling, who sort of they both guided us a lot throughout in various ways throughout this work. So before I dive into machine learning, I'm going to give a brief introduction to strong gravitational lensing. So strong gravitational lensing is the formation of multiple images of a distant source due to the deflection of its light rays by the gravity of some intervening structure. So let's say that here we're on the Earth, and there's 2 galaxies, one right behind the other one. So as the light rays of the distant source pass near the foreground source, they get bent. And so they come to us from different angles. And so as a result, here on the Earth, we see multiple images of the same background source. So it's really similar to what happens if you look at a fish at the corner of a fish tank. If you're going to notice, you can see multiple images of the same background fish. So here's Mr. Mango demonstrating this effect. So as you go to the corner of the fish tank, you can see 2 images of the same fish. So it took me really long to get that video right. As you can, so this is really similar to actual images of strong lenses that we see in the sky. So this is a real image of a strong lens. So here you see 2 images of the same background quasar due to the deflection of its light by the foreground orange galaxy here. So of course, in the case of gravitational lensing, the deflection of light is due to gravity instead of refraction, like in the case of the fish tank. So here's another example of an image of a strong lens. So everything that you can see in this image is a galaxy. But here, there's the background blue galaxy that's being bent, so its image sort of wraps around the image of the foreground galaxy in orange. So that's a really common feature in strong gravitational lensing, this formation of arcs, and that's because of the geometry of the lens. So you can actually reproduce that effect at home with a wine glass and a candle. So I prepared this little video to show you this effect. So you're going to need a wine glass and a candle, and it also helps if you have a little bit of wine and maybe a buddy to drink with so that you don't end up drinking alone. So if you dim the light, as you pick up your glass to have a sip, you can see through the foot of the wine glass, the image of the candle, you see that it wraps around the foot of the wine glass. So this is really similar to images of strong lenses that we see in the sky. So in this analogy, the flame of the candle is the background galaxy whose image is getting distorted, and the foot of the wine glass is the foreground galaxy who's causing the distortions. Okay, so gravitational lensing can be used to study a lot of different phenomena, a lot of different things. So first of all, you can use strong gravitational lensing as a natural telescope. And that's because lensing magnifies the images. So you can use it to study very distant objects, like very distant galaxies, that would otherwise be below your resolution or your sensitivity limit. You can also use strong gravitational lensing to study the matter distribution in the lens itself, so like the foot of the wine glass. And that's because the distortion of the light is due to gravity of the matter that's in the lens. And that's regardless of if it's emitting light or not. So that's very useful for studying things like dark matter in lensing galaxies. And the third thing that, so these are the 3 main things, but the third main thing that you can use strong gravitational lensing for is to do cosmology by measuring H0. So the way that this works is that if you have some time variability in your background source, because the light rays travel through different paths in space-time, those paths can have different lengths. And so that time variability is going to show up as a time delay between the different images that you observe. And so using that time delay and a lens model for the matter distribution in the lens, you can infer H0, the value of H0. So that's become a really hot topic in cosmology in the past, year or couple of years. But whatever the science you want to do, you have to be able to extract some information from your images of strong lenses. So in order to do any science from images like this of strong lenses, you need to be able to model simultaneously two things. First, you need to be able to model what's the undistorted image of the background source, and second, what's the matter distribution in the foreground lens. So it's a little bit like looking at somebody through a funhouse mirror. You're asking what's the undistorted image of the person and what's the shape of the mirror. So to see why these two things completely determine a strong lensing system, we can ask a slightly different question. Let's say that I have the image of somebody and I have the shape of a mirror. It's very easy to simulate the distortions. All I have to do is first take the shape of my mirror, calculate the deflection field, apply it to the image of the person, and voila, I get my distorted image. So the problem is that when I have actual data, I know neither the undistorted shape of the person nor the shape of the mirror. So the problem is that I don't know the inverse function of my simulator here that would allow me to go from the data to the parameters of interest. So to go around that problem, traditionally what people have done is that they basically produce a lot of simulations. So they take a lot of different images of people and a lot of different shapes of mirror, and they produce a lot of simulations until they make a simulation that looks a lot like the observed data. So once they manage to do that, they conclude that it's likely that the little boy that they chose and the shape of the mirror were correct. So that's called maximum likelihood lens modeling, because in order to compare the data with the simulation, we use a likelihood function that we try to optimize. So that optimization process is usually the part where this whole thing gets very complicated. And that's because, well, first of all, like you can imagine, you need to generate millions of simulations to model a single lens. And then second of all, the likelihood function that you try to optimize is very complex. So it's very common for optimizers to get stuck in local minima. And so every time that happens, somebody needs to go in, restart your optimizer somewhere else, and then it gets very expensive in this way. And then the other thing is that every likelihood evaluation is very expensive. And so that makes the whole process very slow and expensive in terms of computational resources and human resources too. So just to give you an idea, like an order of magnitude idea, it's not unheard of to need 2 million CPU hours to model a single strong lens. So it's a very expensive process. So up to now, this has not been such a huge problem because we know of about only 500 strong gravitational lenses altogether. So even if it takes a long time, a couple weeks to model every one of them, it's not such a big deal. But the problem is that in the coming decade, there's going to be a lot of new large-scale surveys that are going to be coming online, like LSST and Euclid and EPISTEMIC, that are expected to discover like few hundred thousand new strong gravitational lenses. Like, for example, LSST alone is expected to discover 170,000 new strong gravitational lenses. So that's really exciting, first of all, because with all those lenses, we're going to be able to we're going to have a lot of statistical power to do all of this science that we're interested in. And then second of all, with such a large population, we're going to be able to find extremely rare events that are very interesting. But then the problem is, how are we going to analyze 170,000 new strong gravitational lenses? So if we assume that it takes about 3 days to do the simplest possible model of a strong lens, it would take a person 1,400 years to complete the analysis of all of the LSST sample. And that's if the person doesn't eat or sleep or have weekends. So I mean, even if you have like 100 grad students to work on this problem, it would still take 14 years. So clearly we need new analysis methods. So that's what motivated us for looking into machine learning. So basically, if we go back to this slide, the problem that we had is that we don't know the inverse function of that simulator here. So we thought, since neural networks are universal function approximators, we could use a neural network to approximate that inverse function of the simulator to go directly from the data to the parameters of interest, and then bypassing the need of producing all those simulations. So more specifically, we looked into convolutional neural networks that are, so I don't know how much, maybe I'm going to not give a super detailed introduction, and I think this crowd is maybe a little bit more expert in machine learning. But so basically the idea is that it's a type of machine learning models that are very well adapted to analyze visual data, so images. And what they do is that they convolve input images with a bunch of filters to produce outputs of interest. And then the value of those filters are learned through a process that's called training, where you feed the network a bunch of examples for which you know what the right answer is. So basically, you fix the value of those filters by finding the values of filters that minimize the distance between the output of the network and the answer that you know. So those have been used a lot in a lot of different sciences. In astronomy, they've been used a lot, and for strong lensing in particular, they've been used a lot specifically for lens finding. So that's more of a classification problem where you would show an image and ask the network, is this a strong lens or not? So we wanted to do was slightly different. We wanted to feed images of strong lenses to the network and then have them analyze those images for us. So basically have the network output the values of parameters that describe the matter distribution in the lensing galaxy. So this is things like the mass of the lensing galaxy, its ellipticity, its angle, its position. So this is more like of a regression problem. Okay, so in order to do that, we had to use simulated data for the training because, like I said, we don't know of a lot of strong lenses, real strong lenses. So what we did, so this is just showing the pipeline that we use for producing the training data. So we started from real images of galaxies, we lensed them, then we applied PSF, and then noise, like random noise, and also Poisson shot noise. We added zero bias, hot pixels, and cosmic rays, and various artifacts. And then finally, we added a bunch of masks to allow us to mask the real images that we wanted to feed to the network if in case they had some artifacts that we didn't want to have to explicitly include in the training data. So once the networks were trained, we tested their performances on 10,000 new simulated images. I'm showing some of them here. So you can see there's a really wide range of different effects like noise, signal to noise, lensing configuration like this one that's like a very poor configuration, or this one that's a very extended configuration, or like some have a lot of masks, some don't. And then also we tested the networks on 9 real images of strong lenses from the Hubble Space Telescope. So this is what we got. Here what I'm showing is basically the output of the network on the y-axis against the true value of the parameter on the x-axis. So the bunch of little blue points are the simulated test data, and the 9 markers are the Hubble Space, the values for the Hubble Space Telescope data. So we can see that we have a really good way of estimating parameters of strong lenses, but the main point here is that this is 10 million times faster than with traditional maximum likelihood methods. So instead of taking 1,400 years to analyze all of the elasticity data, it would take half an hour on a single GPU. So that's pretty good. But if you're an astrophysicist, probably what you're more interested in is something like this. So basically posterior samples of those parameters. So basically what it means is that what you want to have is uncertainties associated with every parameter that you're predicting. So in order to look into how we could have a neural network that would allow us to also predict uncertainties for the parameters it was estimating, we had to look into what are the sources of uncertainties in neural networks. So there's sort of 2 main sources of uncertainties. The first one is called aleatoric uncertainty. So that comes from inherent corruption in the data, so things like noise or blurriness of the PSF. And then the second source of uncertainty is called epistemic uncertainty. So that comes from the neural network itself. So this is due to things like insufficient training or the network architecture, things like that. So in order to capture those sources of uncertainties, we used a method. So there's various methods that can be used. So we used a method that was developed by Yeringal, who is here now, but I think at the time he was in Cambridge. So I'm going to try to describe briefly how this works. The first thing that you do is that instead of having a point estimate for every parameter that you're interested in, you're interested in estimating a likelihood for that output. So that likelihood can have a very complicated form. So what you can do is that you can approximate it by an analytic function and then have your network output the parameters of that analytic distribution. So if you use a Gaussian, for example, for that distribution, then instead of having your neural network output a single point estimate, you would have the neural network output the parameters of a Gaussian for every output of interest. So this is like basically the mean and the standard deviation of that Gaussian. So that's really similar to doing a Fisher analysis for the parameters that you're estimating. So it's important to stress here that this is still a supervised method, even though you have a label only for the mu, the mean, basically. In that cost function here, that's a log of the Gaussian likelihood. You don't need a label for the sigmas. So basically what that means is that they get learned implicitly by the network. So if the network wants to predict a value of sigma that's too large, it's going to get penalized by the log term here, the determinant basically the determinant term here. And if it learns to predict a value of sigma that's too small, then it's going to get penalized by this term here. So it's going to learn to predict just the right value of sigma for every example that you're showing in the network. So that's all good. But then, of course, the neural network can make errors on its prediction of mu and sigma. So in order to capture that source of error, we had to look into Bayesian neural networks. So in a regular neural network, your weights, so this is the values of the filters that you learn, they have fixed deterministic values. So if you feed the same example in the network multiple times, you're going to get always the same answer. In a Bayesian neural network, you basically replace those fixed deterministic values by probability distributions. And so through training, what you want to do is you want to learn what is the shape of those distributions, and they can be different for all the different weights. So the idea is that when you're done training, at test time, you would marginalize over those distributions, and then that would give you basically the output that's marginalized over possible network architectures. So in practice, it's actually very hard to learn to train deep Bayesian neural networks. So what you can do is that you can use variational inference. So yeah, what you would do is that instead of learning the full, free-form P distributions, you would replace them by analytic distributions that have some parameters, and then through training, you would learn what's the value of those parameters. And then you would do that by basically minimizing the KL divergence between the Q distributions and the P distributions. Okay, so in principle, you could choose any distribution for your Q distributions, but it turns out that if you use a Bernoulli distribution, it makes your life a lot easier. So a Bernoulli distribution is either 0 with probability P, or it has some value W with probability 1 minus P. So the P here is a fixed value, and I'm going to come back to how to fix it in just a little bit. But the W is the parameters that you're trying to learn through training. So the reason why this makes your life a lot easier is that it basically boils down to being exactly training with dropout, which is, if you don't know what dropout is, it's just it's a function that's super widely implemented in all neural network libraries in TensorFlow and PyTorch. So it's a very easy thing to add. You don't need to do any extra coding, but you can get your uncertainties basically for free. Okay, so once you combine those two sources of uncertainties, this is an example of what you can get. So what I'm showing here is an example of the uncertainties that are predicted by our neural network. So this is the predicted 1 sigma uncertainty on the y-axis against the true values on the x-axis for a lens parameter. So you can see that we get very good uncertainties that vary from example to example, depending on various parameters like noise or lensing configuration or different things that would influence uncertainties. Okay, but then the question is, how do we know that these are accurate uncertainties? Like, how do we know that if I say 1 sigma, I actually mean 1 sigma? So in order to measure that, what we did is that we looked at coverage probabilities. So the coverage probability of a confidence interval is basically the number of times that the true value falls within that interval. So so ideally, you'd like the coverage probability to be equal to the confidence interval. So for example, for the 1 sigma confidence interval, you'd like the true value to fall within that interval 68% of the time. So what we did is that we calculated those. So here, what I'm showing is, so what we did is that we trained several different neural networks with fixed values of the P parameter that I was talking about before. So the dropout rate P, it's called the dropout rate. So we trained a bunch of different networks. So each group of three bins is basically a different neural network that we trained with a different value of P. So that's the only thing that's changing between the different networks. So the different vertical bins are they correspond to the 68, 95, and 99% confidence interval, and then on the y-axis is the corresponding coverage probability for that interval. So the horizontal line is 68, 95, and 99%. So ideally, you'd like the bins to match the corresponding horizontal line. So what we find is that basically you can use the dropout rate as a hyperparameter that you can tune to calibrate your uncertainties. So is there any question? No? Okay. Yes?
So the parameters are in this just account for those epistemic uncertainties we're talking about, or can you also use this to get a handle on, say, factor effects or whatever else?
So this is going to account, so this includes both the allotropic uncertainty and the epistemic uncertainty. So if you have noise in your data, for example, different levels of noise are going to result in various width of uncertainties. Yeah. Biases are a little bit more tricky if you have systematic uncertainties. But there's, like, we can talk after. There's other methods that I'm looking into right now to be able to interpret this. Okay, so just to recap quickly, so basically this way of incorporating of getting uncertainties with neural network is basically done like this. So basically you would place dropout before every single weight layer, then you would train with dropout on by optimizing the likelihood of the Gaussian here, and then at this time you would keep dropout on. You would feed the same example multiple times through the network, every time with a different realization of dropout, and then collect your outputs. That would form basically a distribution, and then you add the two sources of uncertainties, and then you get the final uncertainties like this. So this is an example of this method applied to real data. So what I'm showing here is, so there's 7 parameters that describe the matter distribution in the lensing galaxy, and then the final parameter is the lensing magnification. So what I'm showing, for every parameter, I'm showing the marginalized posterior, and for that parameter, and then the black curve is that marginalized posterior sampled with an MCMC, and the red curve is what we get with our method with the neural network. So we can see that in every single case, the two answers are consistent, but the uncertainties that we get with the neural network are slightly larger. And that kind of makes sense because you have the additional uncertainty of the neural network itself. So the key thing is that for a lot of applications of strong lensing, it's not that crucial to have extremely high accuracy on the lens model itself, because the bottleneck is somewhere else in the analysis. It's just important to have an estimate of the lens model. But if it was very crucial to have uncertainties that are as small as possible, to have an answer as precise as possible, then it would be possible to use the estimate of the neural network and do something like important sampling to get the actual posterior without having to run the full MCMC chain. Because the key thing here is that to get the black curves, we had to basically run on, it was 256 cores for many weeks, whereas the red curve we could get in 1 second on a single GPU. So the time increase is huge. The time speed up is huge. It's 100 million times faster for this example. Okay. So everything that I've talked about so far, yes.
And what was the MCMC method that you used?
It was MCMC hammer. So it's just a method for.
Is it based on integral safety?
Yeah. Yeah, and that's just for the sampling. The optimizing is also a huge issue in the case of something like that. Because just like I was saying before, because there's so much feature, like there's so many local minima in your likelihood that just getting to the actual right minimum is a huge issue too. All right. So any other question about what I talked about so far? No? Yes.
So if you train a neural network for longer and run it for longer, do you get a narrower distribution?
Yeah. In theory, you could train away all the epistemic uncertainty. And practice, it can be more difficult because you can have various training issues, and it can become more complicated and exponentially difficult in the training. But yeah, in theory, yes, you can do that. Any other question? Yes.
Did you test the neural network on inputs that are outside of its training distribution?
Yeah, we did actually. So what we tested on signal to noise that was much higher. That was on what we had in the training set, and we saw that the errors were correspondingly getting larger and larger. So when it's outside of the training set, but not too far, like outrageously far outside of the training set, then we see the behavior we'd like to see with uncertainties that just get larger. We also tried on feeding images of lenses that were not lenses, where it was just a single galaxy. And the answers that we get were consistent with zero mass in the lensing galaxy, so basically no lensing, with larger errors on the parameters. We also tried the image of a cat, which is clearly not a lens, and then we got answers that were nonsensical with nonsensical error bars. But to be fair, if you did the same thing with a maximum likelihood method, you would also get an answer with uncertainties that are nonsensical, because it's just not a model that makes sense for that image. Yeah. Yes.
So you mentioned this maximum likelihood approach, like the first one, but there's also the neural networks can be seen as a maximum likelihood approach with different models. So I'm not really sure if I understand why you need simulations for the first one, why not for this one, why cannot you use the same algorithm for optimizing the first maximum likelihood problem? So it's not clear to me.
I'm not sure I answered the. I understand the question properly.
For me, they are both maximum likelihood problems, right? It's different models.
I think it's a different likelihood though, because the likelihood you talk when we're doing traditional maximum likelihood lens modeling methods, I think the likelihood that we want to optimize is we're using the physical model of lensing to generate the simulations. I think the problem that you're trying to do when you're doing optimization of a neural network, you're trying to optimize for the values of the weights. So it's slightly different.
So the physical model is not parametric and not differentiable, so you cannot use it.
It's different. It's differentiable. It's just that, yeah, I'm not quite sure what, because, yeah, we can talk about this after, because I'm not, yeah, there's many different issues that come in here. So you could be talking, I'm not quite sure exactly what you're referring to, but we can talk about this afterwards. Yes, any other questions? Yes?
Did you do hyperparameter tuning on another parameter or the drop codes?
That's a tricky question. I mean, there's always a lot of hyperparameters, right? In machine learning, like the number of layers and the size of filters and what?
You can hyperparameter.
Yeah. I mean, like technically, when you're separating your training set into validation set and test set, like you're kind of doing that. But interestingly, what we found is that past a certain level of complexity in the neural network, it didn't really matter that much what the accuracy was. We were getting very similar accuracies for all the models. Like we trained publicly available networks like Inception V4 and AlexNet, and they were all getting similar results to the one that we were engineering ourselves. Yeah. Yes.
Just another comment. Another approach sometimes people make is they make a forward model of the simulator rather than the inverse function, and then that's like a fast approximation of the simulation. Then you can kind of speed up the.
Yeah. So people do that. You still need to train that though. If you want to have an emulator for your likelihood, you still need to train that. And because it's like having an emulator for the likelihood in this case is not really a clever thing to do, because you still have the problem of having the likelihood having a lot of local minima. And then you need to train a different emulator for every lens that you want to model. Whereas with here, you're training only one neural network to analyze all lenses at once. So once you're done training, there's no overhead for any extra lens that you want to analyze. Any other question? No? Okay. All right. So, I guess the contrast is not really good on this image either. But so what I have here, so basically, like I said at the beginning, you're also interested in reconstructing the undistorted image of the background source, because there's a lot of sciences you can do with this. So the way that this is done traditionally is that you basically use, I'm going to take the pointer. So for the background source parameterization, here, you would use basically a pixelated image. So every pixel in the background image would be a parameter. And then when you parameterize your source like that, basically going from the source to the distorted image is a linear problem. So you can basically write down all the parameters that describe the matter distribution of the lens into a matrix, a lensing matrix. And then to go from the source to the lens image, you just need to multiply that matrix. You basically hit the source with that matrix, and then you get your lens image. So because this is a linear problem, it means that you can write the solution for the inverse problem analytically, which is what I've done here. But of course, because let's say, for example, you have a background source image that's 100 by 100 pixel that gives you 10,000 parameters. So clearly, this is going to be an under-constrained problem. So you need to put a prior on the values of the source pixels to regularize the problem. And so if you do that, that folds into the solution here. So this is the inverse covariance matrix of the prior on the pixels of the background source. So we can apply this to the problem that I just showed, this lens image here, which is the one I just showed a couple slides ago. And this is what we get. So like you can see, this doesn't do a perfect job. Like there's a lot of noise that leaks from the observed image to the source reconstruction here. And the reason for that is that when we write this prior on the background source pixels, we're constrained to use a very simplistic prior because we want to keep the problem analytic. So basically, we're constrained to using a Gaussian. So what that does is that it only constrains the 2-point function of the background source. But this is a really poor representation of the knowledge we have about the geometry of a galaxy, just the 2-point function. So because it's only the 2-point function that gets constrained, that's what leads to all this noise leakage in the reconstruction. So the question that we have is, can we do better with machine learning? And so that's something that I did with Warren Morningstar, who was a grad student at Stanford. So what we used is a kind of method that's called a recurrent neural network. So that's a method that's particularly well adapted to treating sequences. So one process that we have a lot in astrophysics is optimization. That can be seen as a sequence because you start from somewhere in parameter space, you take a bunch of steps, and then you end up somewhere in parameter space where hopefully you optimize the function that you want to optimize. So the model that we use is called the recurrent inference machine, or RIM for short. So that's something that Patrick Pusky and Max Welling came up with like 2 years ago. And so more specifically, what it does is that it tries to solve this problem of this form like that, where the y vector is a vector of noisy observations. So that would be the values of the pixels of the observed. So basically, you take the observed image and you unroll it into a vector, and that's what the y's are. The x's are the parameters that we're interested in. So for us, it would be the pixel values of the source image, the undistorted source. F is the physical model that maps your parameters into, onto the observed pixels. So for us, this would be a linear function, so it would be just the lensing matrix here. But in general, this can work for nonlinear problems. It could be not very complicated nonlinear functions. And then M is a vector of additive noise. So if we assume that our noise model is Gaussian, it's really easy to write the likelihood of y given x is just this like that, just a Gaussian likelihood. And so the way that the RIM works is that it tries to solve this equation for x recursively by optimizing the likelihood. So basically, at every step of the recursion, it takes its current best estimate for the values of the x's. It calculates the gradient of the likelihood at that point and uses that to produce an update to the parameter, to the x values. So it works in a way that's really similar to a gradient descent optimizer. So just a quick recap of what a gradient optimizer does. So basically, a gradient optimizer can optimize any function f in a recursive way. So it starts from your current estimate of what the x's are. It calculates the gradient of that function you want to optimize, multiplies that by some fixed constant gamma, and then that's basically your update. And then you keep on going like that recursively until you converge. So what the RIM does is extremely similar. It inputs its current best estimate for the x's. It calculates the gradient of the function and passes that to the neural network. And basically, the job of the neural network is to produce the best possible value for the gamma parameters. And then to help even more improve its estimate of gamma, it has a hidden memory state that keeps track of where it's been in parameter space. And that helps it do an even better job at estimating what are the best possible gammas. So in the case of gradient descent optimizer, you can optimize any function. In the case of the RIM, the function that we want to optimize is the likelihood function. So the way this works is like this. So at every step of the recursion, we have our current best estimate for what the undistorted image of the background source is. We use our physical model to lens this to get a distorted image. We pass that to the likelihood, and we take the derivative with respect to the x's, which are the pixels of this image. Then we pass this back into the RIM, and the RIM produces its next update for what's the best, its best guess for what the undistorted image of the background source is. So the process keeps on going like that until it converges. And then during training, at the end of that, you show the neural network the true value that you should have obtained, and that's how it can learn how to end up at the right place in parameter space. So once the network is trained, you can test its performances on test data, which is what I'm showing here. So this is the same image that I showed at the beginning. This is the ground truth. This is the reconstruction from the RIM, and this is the linear inversion, which are sort of the current state of the art, maximum likelihood based method. So we can see just by eye that clearly the RIM does a lot better. And to quantify how much better it does, I guess it doesn't really show that much. But there's actually a lot of noise around here, and it's much more blurry than this image. So you can quantify how much better it's doing by calculating the coherence spectrum. So that's basically the cross correlation between your reconstruction and the true value. So that's what I'm showing here on the y-axis against scale on the x-axis. And the closer the coherence spectrum is to 1, the better the reconstruction is. So on blue, I'm showing the RIM reconstruction, and in red, I'm showing the linear inversion. So we can see that on every scale, the RIM is outperforming the current state of the art methods, the linear inversion. So this is pretty interesting because this is the first time that we run into a place where machine learning can do better than state-of-the-art methods. So not only does it do it faster, but it can also do better. And the reason for that is, like I was talking about at the beginning, it's because in the linear inversion method, it's really limited because of the choice of prior that we have. But the neural network, on the other side, for the neural network, you don't need to specify explicitly a prior. It can learn its prior implicitly from the training data. So what that means is that it's free to learn a much more complex, much higher point function prior on what a galaxy should look like. And that's what allows it to outperform current state-of-the-art methods that are not based on machine learning. So is there any question about this? Yes?
So for the RNN training methods, would you be trapped in some local field?
You mean for the likelihood? No, that doesn't happen actually. So yeah, we were expecting that, but this is a linear inversion, so it's actually a much easier problem than doing the full optimization. But yeah, it doesn't happen. But we actually are. So I'm going to come back to this at the end. Because we're using the RM to model the lens now, and we don't get trapped in local minima. Yes.
Maybe a naive question if I misunderstood something, but it sounds like what this RN is trying to do is you just train to be a gradient descent algorithm. So why did you need a neural net to do gradient descent?
So the value of gamma is fixed for all your different parameters, where the neural network is sort of, one way to think about it is that the neural network is free to learn a variable value of gamma depending on which pixel it's looking at, and can learn very complex like correlations on different values of gamma. And when you have a two-dimensional image, it's trying to reconstruct. So I mean, technically, it doesn't output like a value of gamma; it's outputting the actual update. Yeah. Yes.
So what is actually trying to minimize for RM?
So the cost function is the difference. Yeah, during training, because you show it the real image that you want to reconstruct at the end. So that's the difference of those two. So the squared difference. It's pixel by pixel. Yeah. The reward is from that. But it's a recurrent neural network, so you input gradient at every step of the recursion. Yeah. Any other question? Yes.
Just for the image you showed before, or
No, this looks really good because this is for 1,000 examples.
And this is for 1,000 examples that haven't been seen before.
Yes, of course. These are test examples. This is not part of the training set, of course. Yeah. I know. No, this is test. This is the test set. Yeah. Any other questions? Yes.
How did it perform outside the training phase?
Yeah. So there you go. All right. So we wanted to test out the robustness of this outside of the training data. So what we did is that we took something that's really far outside the training data. So we took text as the background source. So this is the background source here, and we lensed it, and we added noise and everything, and we tried to de-lens it with the neural network. So this is the linear inversion reconstruction that we get. So this is like with the state-of-the-art, maximum likelihood modeling methods, and this is with the RM. So first of all, it doesn't break it, which is great. So it's robust. It's fairly robust against showing it images of background sources that are outside of its training set. But also you have the same features that you had before. You have like this noise leakage here that comes from the prior choice, and you can see that the error on the reconstruction, the image is much sharper on much of the image here than it is here, except maybe like at the very, very center. But for all the other features that are around it, the reconstruction is much sharper for the RM. Any other question? Yes.
So how do you decide to stop the iteration?
So you can do it in a way that it's going to decide by itself that it's converged, so it's not moving from one iteration to the other, or you can just hard stop it at a certain point. So in this case, because it's a linear problem, it doesn't really need to iterate very much because it's just a linear inversion, right? So after even just 1 or 2 iterations, it's already almost converged. So we let it go for 10, or we tested either between 10 and 15, and it really doesn't move very much. I don't think I have the plot. I can search for it if you want to see after how it changes as function of iteration. Any other question? Yes.
Trying the more naive approach, which is having a network that directly approximates the answer.
Yeah, so that's a lot harder. That's a much harder problem to do, actually. because you go from having, like, you could do that, like in principle, that's like you could totally do that. But going from a big image that has like ring shapes, forgetting about that ring shape and remapping that into something that has a completely different shape, it's a lot harder. So having these kinds of methods that allow you to input some physical knowledge about your problem makes the training a lot faster, and it makes the accuracy much better too. Yes.
So is it right in saying that as opposed to the sort of the full house neural network where it sort of lets it work out everything on its own, including the physics?
Yeah. So you could use, for example, like a UNet to do something like that. Yeah, exactly. So you sort of constrain it to, but it's not really like a hard constraint because you're just feeding the derivative of likelihood as an input, like on an extra channel. So if it couldn't figure anything out from the likelihood, it would just learn to ignore it. So you're just feeding it extra information, say, hey, maybe that's useful. Just, try to use it if you want. Any more questions? No? Okay. All right. So, So another thing that we have in astronomy and in lensing is that we have everything that I talked about so far is for optical images, but we also take images of the sky with interferometers. And so the thing with an interferometer is that what it measures is not an image of the sky; it's actually the Fourier transform of the sky, and it doesn't measure the full Fourier transform. It measures basically every pair of antennas that you have measures a single Fourier transform of the sky. So let's say a single Fourier mode, of the sky. So let's say that we have an image like this in the sky. What an interferometer would measure, for example, is basically the inverse Fourier function of this sampled at those points here that are based on basically what are the antennas that I have and what's the distance between them on the ground. So if you wanted to reconstruct what this sees in real space, you could take the inverse Fourier transform of this, and this is what you would get like this here. So this is called the dirty image, and it looks super noisy, but it's not actually noise. All those side lobes here, they just come from the fact that I have incomplete Fourier sampling of my Fourier space. So it's part of my signal that just gets smeared out everywhere in the image. So here's an example of why this can be kind of a problem. Here I have 4 times this. So this is all the same like sky emission, the same true sky image, but the position of my antennas are different from image to image. So when I do this inverse Fourier transforming of what I measure, what I'm going to get is different. So like I can go from having something that looks like much higher resolution to having like something like looks like much lower resolution if my antennas are all very close to each other. If we want to use a neural network to analyze those types of observation, well, there's a couple of things we could think of. We could try to just use the neural network directly in Fourier space, but because a convolutional neural network uses like small size filters, it's really good at picking up local correlation between things. So it could in principle work, but it's going to be much harder because, in Fourier space, something that's local in real space becomes like really non-local. And so it's going to be really hard for a neural network to learn properly if you feed it data that's in Fourier space. Another thing you could do is to just work with the dirty images, like what I'm showing here. But then the problem is that you have part of that information that's also non-local because of that, convolution with the beam that creates all those side lobes that are part of the signal that have become like non-local. So one thing that we did is that we used the REM once again to basically deconvolve the image to recover the, the right sky emission. So what we did is that, at every step of the recursion, the REM would spit out what's its best estimate for what the true sky emission looks like. And then we'd use the forward model, which is basically just a Fourier transform plus incomplete sampling. And then this is what sort of I'm representing here. So that's the Fourier transform. And then the red points are the places where we Fourier transform that. We pass that to the likelihood, which we form in Fourier space. So basically the Fourier modes that we measure versus the ones that we have from the model. And that's how we form the likelihood. We take the derivative with respect to the pixels here. We pass this back to the REM, and then the process keeps on going like this. So the advantage of something like that, as opposed to an algorithm like clean, for example, if you're familiar with it. So with the clean algorithm, you're not sure that the Fourier modes you would reconstruct are actually faithful to what you actually observed. And most of the time, they're not. Whereas in something like that, because you're enforcing a likelihood that's in Fourier space, you're sure that the Fourier modes of the image you reconstructed are very close to the actual Fourier modes that you observed. So once this part is done, we pass this deconvolved image into the CNN that does the analysis that I talked about before, and that estimates uncertainties. So this is an example of what we get for this method. So this is the same plot that I showed before when I was talking about uncertainties. So this is an ALMA image of a strong lens, and so this is why this was so much faster than traditional methods, because analyzing interferometric data is a lot longer than optical data with traditional methods. Okay, so is there any questions about this part? Yes.
So how do you handle if you don't know the transformation exactly?
Which transformation?
The linear transformation. For example, like in gravitational lensing, you don't know the lens profile exactly for example, in this.
Oh yeah. So basically, so yeah, during training we use, so for the lens, for the background image reconstruction, you mean?
And for example, this where you, for example, if you don't know the something, which point in the Fourier space.
No, you always know that because that's given to you from from just the observation. That's the position of antennas in the real space. So that's always part of you. So that you always know. Yeah. So for when you reconstruct the background, that's what we did. So that's another place where we looked at how well it does under extrapolation. So during training, we always had the right lens model. So we assumed that we knew what the lens model, but of course, when you're actually analyzing data, you don't know that. So during test time, what we did is that we estimated the lens model with the other neural network that I showed before. So at every step, we would basically do the source reconstruction, use that source to do the model, estimate, the model like this. Yes.
Thinking very sparse data, with one object essentially per square.
Yeah, that's galaxy lensing. Yeah.
So I'm wondering for the interferometric case, how applicable is this to wide field interferometry?
So that's, I mean, okay, so I'm going to talk a little bit about that because I'm going to get into, because we're interested in like applying this to cluster lensing, for example, which is much larger scale. So one main challenge is that the data is a lot bigger because you have a lot more pixels. So it's harder because we've been mostly working with like, very small, because it's really small images. If it's on a single GPU, it's really easy to just test a lot of things. But yeah, so we're trying to scale this up right now. I'm going to come back to you. That's what I'm talking about right now. Okay, any other question? No? Okay. All right, so everything that I talked about so far, like you just pointed out, was for the cases where, there's a single object in the lens, it's, fairly small scale, and also the matter distribution in the lensing galaxy is super simple. So it's very smooth. It can be described by very few parameters like a mass, an ellipticity, an angle, a position. But in real cases of strong lenses, like this one here, things are a lot more complicated. Like there's at least 2 galaxies that are relevant in the lens, and there's a lot more stuff going on. So what that means is that we need to have a much more flexible parameterization for the matter distribution in the lens. So one of the things we can do is that we can use a pixelated map of the matter density projected down in 2 dimensions in the lens. So to do that reconstruction, the model that we're exploring right now is that we're trying to use 2 RIMs that work in parallel. So basically the first RIM, its job is to reconstruct this background source. So that's the one I just talked about. So it just does exactly what the other one was doing before. It just tries to reconstruct the undistorted image of the background source. And then the second RM, its job is to try to reconstruct that pixelated image of the projected density in the lens. So they work together because they share the same forward model to produce the lens image. And they share also the same likelihood that they both try to optimize simultaneously. So to train this, we need to have a bunch of galaxies for the lens that are a lot more complex than our usual simple parameterization. So what we've been doing is that we've been using galaxies from the hydrodynamic simulation ILLUSTRISTNG. So these are some examples of those galaxies that we've been using for training this model. But then the problem that we realized is that the ILLUSTRIST simulation is big, but it's not that big. And it doesn't have that many supermassive galaxies that are massive enough to cause strong gravitational lensing. So what we've been looking into is to use variational autoencoders to generate more images of galaxies that are not in ILLUSTRISTNG, but that are similar, that have more complex morphologies. So just quickly, what a variational autoencoder is, it's actually a pretty neat thing. It's basically a neural network that encodes the identity function. So you start from your image, you compress it down to fewer pixels, that's like the Z, that's called the code, and then you decode it back to the same thing. So if you have a really good autoencoder, it would basically just be an identity function. So you would start from so you would get exactly the same thing that you start with. The reason why it's something useful to do is that once it's trained, you can basically sample the code here and then just decode that. And then this way you can get new examples that you didn't have to start with in your training set. So these are some examples of galaxies that we generated like this. So these are not galaxies from the illustrious simulation. These are new galaxies that we've generated with the variational autoencoder. And then with this, we have been training our double RM architecture. So this is extremely preliminary result, and the resolution is really not that great. So that's a shame because it doesn't really show just the details that I want to talk about. But here is the observed image. Here's the model of the reconstruction. Here's the true background source. Here's the reconstructed background source. Here's the true matter density in the lensing galaxy. And here's the reconstruction. So it's not perfect yet. We still have a lot of fine-tuning to do, but it's super promising because the main thing that I want to talk about here is actually all that structure that we see here. We actually managed to reconstruct it here. So it doesn't quite show, but it's really there. And here there's another arm that with the contrast it doesn't show, but that sort of blob here, we managed to reconstruct it here. So that's something that we would absolutely not be able to do with traditional maximum likelihood modeling methods. This would be impossible to get something that's that close to the true, matter density. So that shows that it's a really promising direction to start modeling much more complex lenses. Another thing that we've done, just to test again exactly what this is doing, is that we've been training one of those models to, so basically when there's always two different galaxies in the lens. So this on slightly different scale. So this is basically the observation. This is a lens image. That's what the neural network sees. And that's the density map that it's trying to reconstruct. And at test time, it manages to do fairly well. It reconstructs, every time it manages to know that there's two galaxies in the lens, and it puts them at the right place and everything. But then the question that we have is the neural network just a dictionary lookup, or is it actually learning something new? So basically the question is it always just fitting us back the closest example from the training set, or can it actually understand something about lensing? So what we did is that we showed it images like this when there's three galaxies in the lens, but we didn't do any further training. So it's never seen lensed images that have been, when the lensing have been done by three galaxies. So the thing that's important to stress here is that going from two galaxies in the lens to three galaxies in the lens is extremely nonlinear. So there's sort of no way you would be really able to guess that there were three galaxies involved in the lensing because it's a super nonlinear problem. So we were really surprised to see that in many cases, it manages to see, it's not doing a perfect job, but it manages to see that there are three galaxies in the lens. And so that was very surprising to us. So to us, this is really telling us that the neural network is not just a dictionary lookup. It's actually learning something about lensing. It's learning that correlation between brightness pixels in the lensed image relates to overdensity in the lensing galaxy. So I'm just going to end with this. Because this is a really promising sort of first step towards using this method for modeling a lot of examples of lenses where traditionally we've been having a lot of trouble. So there's a lot of cases where it's been really hard to get good lens models. Like, for example, this lens here that's called the horseshoe that I was showing at the beginning of the talk, we don't yet have a good lens model for it. A lot of people have tried for a really long time to model it, but it's been really, really difficult. Or lenses that are clearly more complex, like this one, on a slightly larger scale, or for example, on much smaller scales, like when we're looking for dark matter subhalos in lensing galaxies. This has been an extremely difficult problem using traditional methods, and so this is a method that could be used, that the machine learning methods could really help a lot making progress in this direction. And another place where traditional methods been having a lot of problems is with cluster lensing. So we're thinking of expanding in this direction and seeing how machine learning can help doing the strong modeling of clusters. So thank you.
We have plenty of time for more questions. You've already answered
Yes.
more than most speakers before, maybe more than all the speakers together.
I like it when there's a lot of questions because I feel that people are it's more interactive. So yes.
So I saw a lot of promise in using machine learning to infer the gravitational lensing. And so what's the problem of inverting that horseshoe lensing using your machine learning model?
So we're not quite there yet. So we're building towards that. That's what we're doing with the double RM. We're trying to use a pixelated map to see if we manage to do a good lens model for it. So with traditional methods, we sort of managed to kind of figure out the lensing, but this leg here, the angle of it is just wrong. So there's something weird going on. So like globally, there's just something. It's not like there's a really small scale subfield. There's just something that doesn't fit. And so we're really hopeful that using machine learning, we can figure out, maybe there's some exotic dark matter structure in it or something. I mean, I don't want to like, this would be like the really, really exciting case. It's probably not that, but yeah, so it would be interesting to see. Yeah. Oh, so this is actually something that I hid under the carpet. So this is not actually the double RM. That's why the images don't look as good. This is a different strategy that we use. So what we did to do this prediction is something that we were doing before we realized that the RM was so promising. What we did is that so we trained the VAE on this image. Well, no, actually, we trained the VAE on these images, so the images of two galaxies. And then what we did is that when we trained this neural network that goes from this to this, we actually trained it to predict the code of this encoded. So we trained the VAE, and then then we stopped the training, so all the VAE weights were fixed, and then we just encoded the answers for here, and then what we did is that we trained the part that goes from here to the code. And then at test time, we can just, all the weights are fixed. So we go from here to the code and the code to the decoded image. And that's how we did it. Because, like I was talking about before, it's going from this kind of geometry, brute force, to something that has a very different geometry was really hard for the neural network to learn. So it was much more useful. So it was really useful for it to learn the compressed version of the image. But that's, the RM seems to be performing a lot better. So I think it's much more promising. But this is all work in progress. So comparison between the two methods is still something that's ongoing. Yes?
Does that RM version be an initial model?
It's now the background source initial model 0, and in the lens, it's a bit tricky because like of the log space, but there's zero mass in the lens, so it starts from 0 to 0 lens. So there's some cost because we show it the real image. That's how it manages to learn. And because we showed the real image, it manages to learn a good pair that allows it not to fall in local minima, which we were very surprised by. But it did really well. Yes?
So I'm thinking about the interferometric maps. Did you have to train then, did you use real galaxies that you then Fourier transform to train, or did you use clean images? Because you made this comparison with clean.
No, we didn't use any clean anywhere. Because it's all simulation, so we have the lenses were generated the same way that I was talking about for the lenses that we used to train the other CNN. So they were real images of background galaxies, and then the lenses were they were.
So I'm just thinking, could you actually just
ignoring
the lensing, just to
yes.
the convolution that
Yes.
people use satisfaction?
Yes, we're doing this right now too. So this was specifically tailored to lensing because it has like a specific geometry that's like very characteristic. But so we're trying to do it for problems where you don't, because with ALMA you have phase information, but a lot of interferometric problem you have only phase closure, you don't have actual phase information. So we're trying to extend this to those kinds of problems where you only have phase closure. Yes.
So returning to the sort of building on Martin's question, applying it to non-ALMA interferometry, if you like.
Yeah.
Where ALMA is a very small field and well behaved relatively. Whereas if you go to a VLN kind of thing or a SK level of complexity, I guess could you take the UV sampling at every time step, essentially, rather than average all the UV data together, you could do it in every 2-second time step and use every observation as your training. Is that feasible? Data volumes are huge.
I mean, I think it really depends on the size. Like, I don't have a number for the size. It can be, like, if it's too huge, it's going to become a problem very quickly.
It's a problem for traditional methods, right?
No, I know. But it could, we're working on it. So, I think it's, like, there's some things we can try. It's really worth looking into, I think, is the bottom line. I'm not such an expert on like those super large scale, but I think Max Welling in his original paper about the RM had an example about SK. So you could have a look at that.
Let's thank Laurence again.